discussing something like time independent Schrödinger equation. Okay, and before that, we also discussed a little bit of about the separable solutions. So, for example, when we have to solve this Schrödinger equation, that is iota hk del psi upon del t is equals to minus hk square upon twice m del square psi by del x square plus v as a function of x psi. Remember, we are taking only those potentials which are independent of time. And given this to us, we wanted to find the solution. So basically what we did, we actually used method of separation of variables. And from here on, we got one function of x and another function of time, which is phi t. And it turned out that this phi t is nothing but it is equals to exponential minus iota e t upon hk, where e is the corresponding energy eigenvalue to this eigenfunction. This kind of solution is called as the stationary state or separable solution. So you'll find this written as separable solution because it uses method of separation of variables, or this is also known as stationary solution or stationary state. Now, why it is called a stationary state, we have discussed. Let us just do it in brief as a manner of recapitulating what we've done so far. So, why this is called as the stationary state? This is called as a stationary state because the norm of this psi does not depend upon time t. In fact, we'll see that uh, physical observables of the state are actually time independent. So just let me give you a little bit of what we've done so far. So basically, like this is how it is. If I do the psi star psi, I know that this is going to be e to the power iota et upon hk times psi star x. Then you should have a psi x and then e to the power minus iota et upon hk. So what you're going to get, you're going to get simply psi mod whole square. Okay, and we see that this time dependence drop out. So I can write here that this time dependence drop out. One more important thing that needs to be mentioned here, and I actually mentioned the previous lecture also, and the same thing we can see for the other dynamical observables as well. So for all dynamical observables, so these are called as stationary state, not only because this norm or probability density becomes time independent, rather uh, they are called as stationary because the physical observables of the state are time independent. Physical observables of the state are time independent. Because after all, you know that the physical observables are either functions of x or functions of p. So after all, like this is all time independent. So basically what will happen if you want to find, let's say, expectation value of q as an operator, then you will get psi star here and you will get q, which is again a function of x and minus iota h ket del by del x, and then you have the psi. In any case, this integration is running over x, and overall these operators are functions of x and p. These operators corresponding to the dynamical observables are functions of either x or p. So after all, this will give you some exponential plus e t upon h ket, and this will give you some exponential minus e t upon h ket. And you'll find that even for any dynamical observable, um, the expectation value remains time independent. So here I'm writing, so expectation value remains time independent. And therefore, the word comes as stationary state. Therefore, the word comes as a stationary state. Also, that I discussed in the previous lecture, that one important thing about it is that E should belong to R. E should belong to R. Why E should belong to R? Because if E does not belong to R, then this particular time dependence will not drop out. Okay, so the time dependence I'm referring here in what you can say, let's say as simple as probability. So let's say probability density I'm defining, and if I don't take E as a function of R and let me take E as from set of complex numbers, then this probability P, the probability density P turns out to be time dependent. Let's see how. Now, in case I take this, so I'll take this as E naught minus iota some gamma. And if I take that, so what I'll get, I'll simply write it first this way. And indeed, there would be psi star as well. And there would be psi as well. And then I have this e raised to power minus et upon hk. So in any case, you know, this is going to be psi x mod whole square. That is absolutely fine. Now you have this e to power iota e star minus of e t upon hk. And I know this e star is nothing but it is equals to E naught plus iota gamma, and E is what? E is nothing but it is equal to E naught minus iota gamma. So eventually, you're going to get something like this. Like you're going to get psi x mod whole square, and this is going to be e to the power iota, and then 2 iota gamma t upon h kit, and which indeed means this. So you can clearly see that this time dependence remains there. So it is no longer a stationary state. So for stationary state, it is essential, it is mandatory that this E should belong to real entities. E should belong to real numbers. E cannot be any, E cannot belong to set of complex numbers. Further, we saw that this particular psi x satisfies something called as time independent Schrödinger equation. This particular psi x satisfies something called as time independent Schrödinger equation. This is something that we have done previously as well. Just I'm revising it for you. Time independent Schrödinger equation, which is an eigenvalue equation given by minus hk square upon yz, and then you have this del square psi upon del x square plus vx psi is equals to e psi, and in terms of operator, I can say this h ket psi is equals to e psi. Here h ket is the Hamiltonian operator. An important assertion from here can be drawn that these states, these stationary states, are the states of definite energy. By definite energy means I have no uncertainty in Hamiltonian in finding the what you can say variance of this h. Uncertainty or variance of h would be 0. So let us see. I have already stated that, but let me just recapitulate uh, for you. So basically, if I try to find this h, this expectation value of h, I'll get something like psi star h get psi dx, and which turns out to be e times psi mod whole square dx, and is simply equals to e. And had I found h square, this expectation value turns out to be e square. Now, if I want to find the variance in h, that would be simply root over e square minus of e square, and which indeed is 0, which implies that the that in the statistically it implies that this particular distribution of h, if at all I make a distribution in h, then this distribution in h does not have any spread. Okay, so every measurement of the total energy is certain to return the value e only. So basically, you don't have any uncertainty in measuring this h. So basically, variance is 0. It implies that this separable solution only it is um, true for the separable solution. So this separable solution, or you can say this stationary state, has a property that every measurement of the total energy, if I take, I'm going to get a definite energy. Now, another important thing is that a general solution can be written as general solution. If I want to write general solution, the general solution can be written as the linear combination of linear combination of some, you can say, uh, linear combination of stationary states or separable solutions. So how to do it? So for example, if I solve time independent Schrödinger equation, I'll get some psi1, psi2, psi3. All these are time independent. But if I want to find what would be the values of these functions as functions of both x and t, it will be equals to something like psi1x and then e raised to power minus iota even t upon h ket, where even a2, a3 are the associated, you can say, uh, these energy eigenvalues, you can say, or you can say these are the separation constants. So if you remember, when I was doing this thing like method of separation of variables, I introduced this kind of constant. So in totality, if I want to write, because the Schrodinger equation is linear, so if psi1 is a solution, psi2 is a solution, then any linear combination of psi1 and psi2 is also a solution. So therefore, I can assert my case that even if there are infinitely many solutions to a particular problem, and let's say the wave functions I get from time independent Schrodinger equations are psi1, psi2, psi3, dash dash dash, then I know from my calculation that at any future time, if I want to write wave function, it can be written in this manner. And if I want to write all these states, let's say psi1, psi2, psi3, if I want to write the general solution out of this using these states, that is psi1, psi2, psi3, I can write it in this manner. However, I told you one more important thing that let's say, let's say I'm talking about a particular stationary state. Let us say I am talking about psi1. Psi1 as a function of x and t, you can find this as psi1x, and I can write it as minus even t upon h ket. Fine. If I want to find the probability density, if there is only if the entire quantum mechanical system can be expressed by this wave function, then I would find that this norm would be time independent. It would be time independent. However, if I take a linear combination of psi1 and psi2, then it may not be the case. It may not be the case. See how? So if I take a linear combination of it, let's say now my quantum mechanical system is expressed, let's say at time t equal to 0, in terms of linear combination of two stationary states, that is, let's say psi1 and psi2, then do you think that this remains to be a stationary state? No, indeed it does not. See how? So I have already taught you, but let me just give you an example. Let me just revise it for you. So it will be like E1 t upon h ket, and then this is plus C2 psi 2, and this is e to the power minus E2 t upon h ket. And this brings us to this thing, psi star psi. And eventually you will find with all sort of calculations that I've done previously. Okay, and here for simplicity, I'm taking C1, C2 to be real, and the psi I is to be real. So that just for the simplicity. Okay, so this will be C2 square, C2 psi 2 square, and then there I'll get something. I'm leaving this exercise for you. You can do it on your own. You will get some time dependent factor embedded in the cosine function. So basically, this time dependence does not drop out. Okay, so indeed it is not a stationary state. So linear combination may not be a stationary state. This here you have time dependence. However, if a quantum mechanical system is entirely expressed in terms of psi1, then it is fine. But if it is expressed in terms of linear combination, then one can see that this probability density oscillates sinusoidally. You can see that there's a sinusoidal function here. So it oscillates sinusoidally with the angular frequency omega given by E2 minus E1 upon hk. And certainly, it is not a stationary state because of this time dependence. Now, further, I went on to state three very important results about. So, three very important results. In fact, four very important results. Four important results about these stationary states. So, we already have discussed it, but let me just revise it for you. So one of the first thing was that there is no such degeneracy involved when we discuss one-dimensional potentials. The first thing that we were actually the first thing that we were discussing was this, that um, that if I'm talking about bound states in one dimensions, so if I'm talking about bound states in one dimensions, then these bound states do not have any degeneracies. Specifically, I'm talking about one dimension. Okay, so there's no such degeneracy involved. And degeneracy, you know that if two or more wave functions can be associated with a single energy eigenvalue, then these are degenerate states. So I already told you, let's say, uh, how did I prove this particular thing? Just a little bit of recap of it. So suppose that there is a degeneracy and psi1 and psi2 both correspond to the same energy eigenvalue, that is E. And if it indeed is the case, then you know that these are going to satisfy this. So I wrote something like 2me upon h ket square. I just gave a notation this thing, and 2mv upon h ket square. I'm going to give notation this. So basically, this is going to be psi1 equal to 0, and this is it. Okay, now this is one thing. Now, if this is the case, what I can do, I can multiply this with psi2, I can multiply this with psi1, and then indeed I'm going to get one important thing, that is psi1, sorry, psi2, psi1 dash minus psi1, psi2 dash dash is equals to 0, and which means that I'm talking about this thing, that is psi2, psi1 dash minus psi1, psi2 dash is a constant. And I know that as x tends to infinity, psi2 and psi1 both tend to 0. For all normalizable state, this is the truth. So C goes to 0, and which would imply that this particular thing, when solved, will give you that psi1 is equal to k times psi2. If you solve it, you'll get psi1 is equal to k times psi2. And which indeed means that these wave functions are not different, rather they're one. So basically, we were thinking that psi1 and psi2 are two different functions uh, associated with the same energy eigenvalue, and we assume that let it be the truth. But what we got instead, we got that psi1 is equals to k times psi2. Indeed, they're linearly dependent to each other. Okay, so our assumption is false. Our assumption is false. That is, psi1 and psi2 cannot be two different states corresponding to the same energy eigenvalue. Rather, they are same. So you can find that for bound states in one dimension, there's no such degeneracy. Now you would be thinking, where did I use this bound state? See, when I'm assuming that as x tends to infinity, psi1 and psi2 should tend to 0, it implies that psi1 and psi2 are bound state. If 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 as even as x tends to infinity, psi1 and psi2 are not going to 0, that implies that these are not bound states. So basically, for bound states, it is a compulsion that psi x must tend to 0 as x tends to plus minus infinity. Similarly, we also wrote one important result, that was that the energy eigenstates psi x can be chosen real, can be chosen real. Okay, why I'm telling it energy eigenstate? See, because these are satisfying this equation. Okay, so therefore, because these are satisfying this energy eigenvalue, so these are called at times also referred to as energy eigenstates. So don't be confused. They can always be chosen real. Okay, this is something that we have done in the previous lecture. Also, an important result was that if potential is symmetric, if the potential is symmetric, or you can say the potential is even, then the wave function has a definite parity, or the wave function or eigenfunction or eigenstates can be chosen to be even or odd. Okay, this is an important result. So if potential is even, then eigenstate can be chosen even or odd. So let us see how. So first thing first means energy eigenvalues psi x can be chosen real. How? See here. So from here, this is the first result. See, the psi double dash plus epsilon nu psi is equal to 0. Now understand whether I take the conjugate and then take the double derivative, or I take a double derivative and then take the conjugate. This is not going to, like these are equal things. So basically, instead of this, I'm going to replace this. So if psi is a solution, then psi star is also a solution. Okay. Now, if psi is different from psi star, which indeed it is, then definitely it defines a degenerate solution. It defines a degenerate solution. So basically, psi star and psi different. Now, what I can do, I can make by using this, I can make some linear combination. So let's say if I want to find, uh, if I want to write, let's say psi, let's say one notation I'm giving psi r, and then I'll let you know why I'm using this. I can define this. Can you not see that this is a this is a this is a real function, right? Because psi and psi star, when they're added, they will give a real entity. And another way, you can also create this. So from the linear combination of psi and psi star, one can generate real eigenvalues, what you can say, real eigenstates. So energy eigenstates, that is psi x, can always be made real. I mean, they can always be chosen real. I'm not saying they will always be real, but they can always be chosen to be real. Okay. In particular, if we are dealing with the bound states, now we know that in bound states, there is an absence of degenerate states. So there is an absence of degeneracy. That is something that we have established previously. Since there is absence of degeneracy, what happens is that these real solutions are equal basically by some constant. Okay. And this constant also need to be real. So basically, this is the case. Okay, I hope it is clear. And if you just think about it, what is this? This is nothing but this is equals to real part of psi, and this is equals to what? This is imaginary part of psi. If you just think about from your complex analysis, you can like you can understand this is nothing but this is the real part of psi, and this is the imaginary part of psi. So if I want to write my psi would be what? It is equals to psi r plus iota psi im. And at max, what I can do, I can write this as psi r plus iota c psi r. I already know that this is equivalent to writing 1 plus iota c psi r. And after all, what is 1 plus iota c? It will be equals to something like this. This is the magnitude times e raised to power iota, let's say theta. Let's say I'll write theta. Okay, so psi is basically nothing but it is equals to something like root over 1 plus c square e raised to power iota beta times psi. Okay, so basically any solution to the bound state up to a phase is equals to a real solution. So up to a phase, it is after all equals to a real solution. Okay, so any general solution up to a phase is nothing but up to a phase is a real solution. So after all, one has to understand that for stationary states like eigenenergy states psi x, they can always be chosen real. This is something that I've written here. Now, if I just want to do one more thing, if I just want to elaborate on the last thing, that is if Vx is such that V of minus x is equal to V of x, then let's see if I use psi x. Psi x is a solution for this. So I'll write psi double dash plus epsilon mu times psi equal to 0. Okay. Now, if I replace, if I just write here x and if I just write here x, now if I replace x by minus x, what is going to change? So psi double dash minus x plus epsilon minus nu x, it will remain the same because by nu minus x is equal to nu x only. Understand what is nu? Nu is nothing but is equal to 2mvx upon h square. Now, if v is an even function, then nu minus x is nothing but it is equal to nu x only. So, and here you have psi double dash minus x. So what it means? It means that that psi x is also a solution, and in fact psi minus x is also a solution, right? You can see here. So it turns out that psi x is a solution, then psi minus x is also a solution to this Schrödinger equation. So basically, if psi x is one solution, I'm writing it here, is one solution, then psi minus x is another solution. And in fact, from this, I can always make two parts. Okay, so I can make two parts. That is, one is like, I'll write it as symmetric, that is psi x plus psi minus x upon 2. And other one is psi odd part, or you can say anti-symmetric part, that is psi x minus psi minus x upon 2. Now, if you just think about this, so if I just do psi x like this, if I do minus of x, then what I'll get? I'll get psi minus x plus psi x upon 2. Clearly, this is even. And if I do, clearly this is odd. So if Vx is such that V of minus x is equal to Vx, then corresponding eigenstates, energy eigenstates, are either even or odd. And this is what we were claiming. In particular, when we are dealing with the bound states, what is going to change? I know that in bound states, for the bound state, there is absence of degeneracy. Since there is absence of degeneracy, so indeed this has to be like this. Psi of minus x in up to a constant must be equal to some psi x. Basically, I'm not saying that identical, but up to a constant they must be equal, or up to a phase factor as I mentioned above. So they must be equal. If they are equal, so if I just replace x by again minus x, what am I going to get? I'm going to get this psi x is nothing but it is equal to c times psi minus x, which equals to this. I know that wave function, if I'm doing it, if I'm not taking potentials to be infinite, they are not supposed to be 0. So basically, it implies that c square has to be 1. So implies that c has to be plus minus 1. So either psi minus x is equal to psi of x, which implies evenness, and if psi, otherwise it is psi equals to psi x, which implies odd. So any one-dimensional bound state solution, any one-dimensional bound state solution with an even potential, that is V minus x equal to Vx, or you can say symmetric potential, must be either even or odd under the transformation x to minus x. Okay, so this is something that I've written here and have summarized each of these things. Now, a few important things that we are going to take in the next lecture as well is the nature of the spectrum. And just give me a minute. So the next thing, as I mentioned, I'm going to do with I'm going to write a few points regarding the nature of the spectrum. We're going to take this lecture in detail in next lecture, but right now I'm just writing nature of spectrum. Okay. Now see, we know that this Schrödinger equation, I can write it in this form. Okay, this is something that I can do. I can write my Schrödinger equation in this form. Now, now here we know that psi x is always continuous. This is the condition from Max-Born interpretation. We know. Okay. Now there can be three possibilities regarding the potential. So regarding the potential, we can have three possibilities. Possibility number one, that Vx is continuous. So let us say that we are discussing a case where your Vx is simply continuous. Okay. So if Vx is a continuous function and psi x is a continuous function, so what will happen? This product will be continuous. Constant times a continuous function is also continuous, which implies that psi double dash is also continuous. And which indeed requires that psi dash must be continuous. Because if psi dash is discontinuous at a point, then this will not remain continuous. Okay, so psi dash must be continuous. Now, case number two, which may arise, that let's say this Vx is now has some finite jumps. Okay, this Vx may have some finite jumps. Okay, so if Vx has some finite jumps, or you can say finite jumps means some finite discontinuities. Then obviously psi dash will also be discontinuous or will bear some finite discontinuities. Why? Because after all, see, psi dash is what? It is equals to psi double dash will also bear some finite discontinuity. See here, if Vx has some finite jump, so uh, all these jumps at all these discontinuities is psi x is getting multiplied, so it will result in psi double dash having some finite discontinuities. But do remember that since psi double dash is defined, so your psi dash cannot have discontinuities. Now I'm writing it for finite discontinuities. Okay. See, again, understand. If Vx has some finite jumps, means it has some finite discontinuities. Okay, it has some finite discontinuities. Then what will happen? Psi double dash will also have some finite discontinuities. But if psi double dash is defined, if it is defined, uh, then what happens is that psi dash cannot have discontinuities, because if psi dash have discontinuity, then psi double dash will have a problem. However, for the cases of infinite discontinuities, we'll find that even the psi dash becomes discontinuous. Okay, and there is some finite jump. So basically, precisely for the cases of Dirac delta function, so if Vx, what you can say, bears some infinite discontinuities, there you may have the discontinuity of psi dash. I'll give you examples also, don't worry. So if Vx is, let's say two examples I'm taking. So first, let me divide it by saying that, let's say Vx contains some Dirac delta function. Now, if it contains Dirac delta function, so if you remember, let's say, even if you don't remember, I'm going to give you result directly, so you just remember it. Let's say if the particle is subjected to a potential which is V is equal to V naught Dirac of X, let's say minus attracted Dirac delta potential, then correspondingly the the eigenstate would be something like e to power minus of modulus of X. And clearly, this is discontinuous at X equal to 0. This particular wave function is discontinuous at X equal to 0. This is how it is going to be. And you know that psi x would be simply e raised to power x at x greater than 0 and e raised to power minus x for all x less than 0. And if I want to find psi dash would be simply e raised to power x for all x greater than 0 and minus e raised to power minus x for all x less than 0. And if I want to find the jump discontinuity at x equal to 0, so if I want to find what will be the jump discontinuity at x equal to 0, clearly the jump discontinuity at x equal to 0 would be around 2. So what you can see, I have given you an example here. Just don't bother about how this would come. This is something that we are going to see, but right now just take as an example. I have not even normalized it. Fine. So this is like not non-normalizable solution for right now, just to keep things simple. So if Vx contains a Dirac delta function, I have given you an example that before this, I have given you example that if Vx has some finite jumps, no, this does not have a finite jump. You know that if it is Dirac delta function, then this is infinitely long spike. Is an infinite long spike. Okay, so if Vx contains Dirac delta function, then you have this finite, it is an infinite discontinuity. This is not finite jump. Now, if it has infinite discontinuity, then there are two cases. There may be the case of Dirac delta function. There may be case of some hard wall kind of thing that I'm going to write later on. So if Vx contains Dirac delta function like this way, then what is suggested that even the psi dash is discontinuous. That is fine, but the discontinuity in psi dash is finite. So I'll write it here. Now here, in this case, psi dash indeed is discontinuous, but psi dash has finite discontinuity. Now the fourth case is again the case of discontinuities, and the case can be like if Vx contains hard walls. And what do I mean when I say hard wall? So it is like I want to suggest that it is a potential which is finite to the left of some point, and for all x greater than a, the potential is infinite. Then we'll say that x equal to a is the hard wall. Okay, and since Vx is infinite, so your wave function for all x greater than a would be simply 0. Okay, now here what will happen? Here again this problem of discontinuity will appear, and psi dash will again have some finite discontinuities. See how? So let me take an example from here. If you remember, it is fine. If you don't remember, then I'll write it for you. So if you remember, if I have an infinitely deep potential well, so let's say here your Vx is infinite, here your Vx is infinite, and here your V is simply 0, then you know that the solutions to this is given by root over 2 by a. If it is like x equal to 0 to x equal to a, sine of, and let's say I'm writing ground state, pi x upon a. So I'm writing the ground state. Okay, now to the right of a, the wave function is simply 0. So even if I take the derivative, it will be 0. But to the left of it, it is equals to root over 2 by a. pi upon a, cos of pi x upon a, which is again cos of pi 0 upon a, which is simply. So you'll find that there is a finite discontinuity. So psi dash has some finite discontinuity at x equal to a. So what will happen? If Vx contains hard wall, then at the hard walls itself, that is at x equal to 0 and at x equal to a, there will be discontinuity in psi dash. So this actually a little bit changes our understanding of the bond interpretation of physically realizable wave functions. Okay, indeed they are not physically realizable wave functions, but understand that these in these problems, like in these problems. So for example, if I say, will particle in a box be a physically realizable situation? Indeed, it is not. Okay, but we start our curriculum from there. So understand the point that the first thing that I need to mention here is that the bond interpretation for physically realizable functions stands still there. That is, both psi and psi dash are continuous, are continuous, unless unless the potentials have some Dirac delta functions or hard walls. So in these two cases, the psi dash will be in a finite discontinuity. Okay, so if Vx has finite jumps, then it is not a problem. So if Vx has a finite jump, then it is not a problem. Then psi dash cannot have discontinuity. Psi dash here, for this case, psi dash uh, is continuous in fact. So psi dash will be continuous with some non-continuous derivative. Why non-continuous derivative? Because psi double dash will have finite discontinuity. So psi dash will be continuous, but psi double dash will have will be non-continuous, because you know that has some finite jump. Then indeed from the Schrödinger equation you can understand that psi double dash will have discontinuities. But if Vx has some finite jumps, then psi dash will not have discontinuities. This is something, these cases we are going to see as we are going to discuss one-dimensional potentials in detail. Right now I've just given you a little bit of sketch of it. Okay, I hope this is clear. Let us consider a problem a little bit of. So let us consider the case of ball bouncing back of Earth. Okay, now quantum mechanically we are assuming right now. Okay, and I'm giving you just a case. We are going to see this case in greater detail when we are going to see the approximation methods. But quantum mechanically, we are considering Earth to be a so Earth to be a infinitely hard sphere. Infinitely hard sphere. Let us, and we are also considering the surface of the Earth as the origin. That is, it implies that P0 would be some infinite. And a linear potential elsewhere. Linear potential elsewhere. That is Vx is equal to some mgx for all x greater than 0. In fact, minus mgx, sorry. Now, we want to know which of the following wave function is physically admissible for this problem. Okay, so this time I'm giving you some options to think upon. Okay. Now, which of the following options do you really think that that are going to reflect this problem and will give you a wave function which is physically acceptable according to this problem? So according to this problem, so according to the statement, we understand that Earth has been taken to be a hard sphere, and in fact, it is taken to be origin. So I'll write that Vx is such that it is given to be infinite at x equal to 0, and for all x greater than 0, it is minus of mgx. Now, since at x equal to 0, you have a hard wall. Since at x equal to 0, we have a hard wall. So clearly, psi dash would be such, psi dash will have some finite discontinuity at x equal to 0. One thing is very much clear. Finite discontinuity at x equal to 0. This is clear? Okay, what else can be thought about? Another thing that can be thought about was that for all x greater than 0, psi x must be some finite value. And at x equal to 0, the wave function should be infinite. Wave function should be 0 because the potential is infinite. Because at x equal to 0, the potential is infinite, so wave function must be 0. So this option cancels out. In fact, this option also cancels out because this is clearly singular at x equal to 0. This option is singular at x equal to 0. So it is 1 upon x, so it will tend towards infinity as x tends to 0. And this is equals to 1, so this gets cancelled. Now you have two options. Either it would be this or either it would be this. Okay. I hope it is clear. So minus x e to power kx and minus x e to power minus of kx square. These two are two likely options. Okay, these are two likely options. Okay. Now let us think about this option. That is option number C. Now what does option number C says to us? It is equals to x into e to power kx. Indeed, psi 0 is 0. It is fine. And psi x for all x greater than 0 is also fine. But do think about this. Is it going to, as x tends to infinity, the psi x goes towards infinity. Okay, this psi x goes towards infinity. For physically realizable wave function, we must have this thing that as psi x tends to infinity, as x tends to infinity, your psi x must go to 0. So the most appropriate wave function that you can select for the above would be option number D. I hope it is clear. So you have to select a wave function which is physically admissible. And for physically admissible wave functions, or you can say uh, for physically admissible wave functions, your x tending to infinity, your psi x must tend to 0. Okay, so indeed, option number D looks very promising. So option number D would be the correct answer for this question. Okay, so all these things we are going to take in greater detail in next lecture. Till then, take care. Bye-bye.